Now, there is an equation for work. So the amount of work done and therefore the amount of energy increase that the system will experience is given simply by this equation. So we have the work here for W, and then we also have force, and then parallel displacement. And we will be using this interchangeably with distance at times, but either way, that would just be the change in position, remember. So the definition of work, just to write it out, we have the work is equal to the force that's applied multiplied by displacement. Now, notice that it says parallel here. So this displacement must be parallel to the force. And what that means essentially is, let's say we have a force. We'll just say it's going this way to the right. The displacement of the object is either going to be parallel to the right, or it could be anti-parallel. So it would be moving to the left. But either way, those would be considered parallel displacements. So if that is true, if the displacement, no matter which direction it's going, is parallel to the force, then work will be done. So the work is the product of the force applied, which moves the object a parallel displacement. Now there's a couple points to consider about this equation. Now, if the object that is experiencing the force does not move, so the displacement here would be 0, then no work is done. The energy of the system would be unchanged, and it would be considered a state of equilibrium. So we have the example with the acrobat here. He's not moving. There are forces. Now, there's nothing horizontally, but there's always those vertical forces present. Let's say if you are on a surface, which he is, so we have the perpendicular, the normal force going up. He's not moving. He's not accelerating, though, vertically. So this normal force would be equal in magnitude, let's say, to the weight, the mass times gravity force. So there are still forces there. However, the energy of the system is still unchanged. Since there's not an unbalanced force. There's not a non-zero net force. Everything is balanced at 0. As a result, there is no distance traveled or displacement occurring. And since the displacement is 0, if you recall the work equation, since displacement is 0 there, work is going to be equal to 0. So, the energy of the system, in this case, the initial, will be equal to the final. Now, 3 important examples of work. We're going to go through very quickly. We've got positive work, negative work, and then 0 work. So for positive work, this is when the object moves in the same direction as the direction of the force. So an example would be if the force and displacement are in the same direction, then the work will end up being positive. So the work done is going to be greater than 0. As a result, you would increase the energy of the system. So you can see down here, we have our force. And this little arrow here, remember, that just means that it's noting that force is a vector quantity. It's not necessarily indicating the direction. Focusing on this arrow here, this vector, it is saying that the force is going to the right. You'll notice that this matches displacement, which is also to the right. So this object is moving rightward. Since that is the case, remember that work is equal to the force. It's the product of the force and the parallel displacement. Here we see that the force and displacement are parallel. And when they go in that same direction, you end up with positive work. So if we wrote this equation, or actually first I want to mention that, what we're seeing here, since the energy would be increased in this system, work is being done. If you consider, and we have an acceleration, let's say, acceleration is going to be going that way. We have an initial velocity here that's less than the final velocity. So velocity ended up increasing, and that's because work was performed and energy was increased in this system. So in this case, we have our initial energy. We had work done. It's positive. You would end up with a total final energy greater than the initial here. Now the opposite here for negative work, what we have is the object is moving in a direction opposite the direction of the force. So if the force and displacement are in opposite directions, then the work will be negative. It's going to be less than 0. So to show you that in an equation, we have our initial energy minus, we have negative work being done. So that final energy is going to be less than the initial. We're taking energy away from the system through this outside work. So the example here, we have our force moving to the left this time. The displacement is moving to the right. Now they're parallel, but the force is opposite the direction of the displacement. So when that is the case, you're going to be decreasing the energy, the final energy of the system. And the only way to do that is by there being negative work as a result. So let's say we have this initial velocity going in. It's going to end up greater than the final velocity here. So we see acceleration sort of decreasing in this case. And then, if you think about the type of force that's present that could cause this, something that we just learned about is friction. So if this was given a push, let's say, but this is a rough tabletop, then the friction force would be opposing that motion. So this could be force of friction here, and that would be the cause of the negative work being done on this object. Now you can also have zero work being done. So that's if the object moves in a direction perpendicular to the direction of the force. So we could say that the force and displacement are at right angles here. There is no force being applied in the parallel direction of displacement. So displacement in this case is horizontal, but the force is vertical. So there is zero work happening in this example. So the energy of the system in this case is unchanged. The initial will be equal to the final. So no acceleration occurs due to the fact that no component of force acts in the direction of displacement. No work is done by the normal force or the force of gravity. Remember, we have our normal force here, and then there's also the force of gravity. But the net force there is 0. So no matter what, the forces here are perpendicular to the displacement, so no work is done. So just to recap, positive work increases the energy of a system, and this is when the object is moving in the same direction as the direction of the force, so the displacement and force are in the same parallel direction. Negative work is when the force and the displacement are anti-parallel, and that would decrease the energy of the system. And zero work is when the force and displacement are perpendicular. So that would result in zero work being done on the system, and that final energy would be equal to the initial. Now the units of work and energy, just really quick, it's the joule. Now where that comes from is it is in honor of James Joule, who made critical contributions in developing the idea of energy. So we call the unit of energy the joule. Now what that actually is, and you never need to write this down, but it's the Newton meter, which if you recall from the last unit, a Newton is kilograms per meters per second squared. So technically all of that combined over here, we have the kilogram meter per second squared times meters gives you this. But we're just going to keep it simple, and we're going to call it the joule. That is the unit that is standard here. And so for the practice problems, remember, let's log in to hellosmart.com. We'll give a moment for the class ID to load here. 450171. Dan's already in. So take a moment to do that, and then there are about 9 questions to work through that we'll go over. For the first question here, it looks like it was unanimous, so let's see if you were right. All of you said that the answer was C, which is correct, 240 joules. So it looks like we're pretty good on using the work equation here. It's just a force times displacement, both of which were given to you in this problem. Second question. It says that the 24 Newton force is applied to an object that moves 10 meters in the opposite direction. Let's see what you have. Again, it was unanimous. All of you said it was A, which is correct. So good. It looks like you all caught the little hint here. We've got the opposite direction. So in this case, the displacement here moved 10 meters in the opposite direction. Therefore, it was negative, giving you negative 240 joules. So good. Third question again was unanimous. So let's see, you all said it was C. 0 joules, good. You saw that the object is stationary. Therefore, no work is done in that case since there is 0 displacement there. 0 meters, the product would be 0. Okay, so number 4. All right, for the next one here, also unanimous, you all said B, which is correct, 5 newtons. You did that quick rearrangement of the work equation, good. So force is equal to work divided by displacement, giving you 5 newtons. The next one here, you all said A, which is also correct. So great work all around. Again, just rearranging that equation, and we are plugging and chugging at this point. Now the next one, we have the boy riding the bike. Okay, we're given speed. This one was a little more split. We've got speed given, we have a force, and we have time. So we're not clearly given a displacement. Most of you said that the answer was D, 30,000 joules, which is correct. So the way you get that, since you're given speed and time, you can use the speed equation from way back in the beginning of the year to figure out that displacement or distance. So again, the speed equation is that speed equals distance over time. Just rearranging it to solve for distance here is speed times time, which we're given. We're given 3 meters per second, and then 100 seconds gives you 300 meters, which you can then substitute in for the displacement, giving you 100 newtons times 300 meters, gives you that 30,000 joules. So just be careful when you see what is given that you need to think about, is there still a way I can figure out what I need for the equation? All right, the next one here is similar. So just to show you again, we're given speed, we're given time, and we're given a force. So remember, you can use the speed equation to get your distance, your displacement there. Plug it into the work equation. So what you end up with is a displacement of 120 meters times the 350 Newton force that you were given, gives you 42,000 joules. So D was the correct answer there. Most of you got that. And then when we get to 8 and 9 here, answers are a bit more split. So this one is about a 50-50 split. So a book is held at a height of 2 meters for 20 seconds. How much work is done on the book? So let's take a look. The answers are pretty much split between A and C. So something to keep in mind, the object remains stationary. Therefore, no work is done. It's held at a height. Remember, if there is no displacement, then your work ends up being 0. The work equation here, force times displacement. Now it's held at a height of 2 meters, but that's not a displacement. A displacement is a change in position over time there. or change in position, sorry. So there is no change in position. It is just being held. Therefore, displacement equals 0. And since that equals 0, then work equals 0. So the correct answer was A for this question. Now the last one here, a few different answers. Some of you said A, some said C. I see a couple I need help, which is fine. So let's go over this one. So we have a barbell of mass m is lifted vertically upwards at a constant velocity to a distance h by an outside force. How much work does that outside force do on the barbell? So we're given a hint. Do a free body diagram to determine a formula for the outside force, so your force applied. Then use the formula for work. Work equals force times parallel displacement. So we have our work equals Fd. Now let's say we have our barbell here. Let's draw the free body diagram. We know that it is being lifted vertically upward. We'll call that the applied force. It says constant velocity. So acceleration in that case will equal 0. So since acceleration equals 0, we know that the applied force is going to be equal to mg. So something here, we're looking at the answers on the left here. Now, there's nothing here saying anything about applied force being this equation. But we know that the applied force here is going to be equal to mg since the acceleration is 0. Remember, when you go back to the last unit, our F equals ma Newton's second law equation here, we have our applied force minus mg on the left side of the equation is equal to ma. Since acceleration is 0, all of that cancels out, where the product is 0. As a result, force applied equals mg. So taking a look at the work equation here, this force applied there, let's say we write it as work equals, okay, our force is an applied force times displacement. You can sub in mg. Now that's starting to look more like what's over here. Now we also know that is lifted vertically a certain height. So it's moving up. The displacement in this case is being called height, h, instead of displacement. So you can also replace that with h. Now that's starting to look a lot more like what's over here. So we have mgh. The only question is, would it be negative or positive? Once you get rid of these choices here, we know it's not going to be mg or negative mg because that's only describing the force, the applied force. However, how do we know if it is positive or negative work? It looks like those of you that chose responses either chose A or C, and we just canceled out A, so it looks like everyone else narrowed it down to C, which is correct. And that's because, remember, work it has to occur in a parallel with the displacement. So we have our applied force upward and the height upward. Now they are parallel, and they are parallel in the same direction. And when it's the same direction, remember that would be positive work. If it was opposite directions, let's say it was brought downward, that would have been negative work. But in this case, we have positive work. So C would be the correct answer there. Okay, so all right, so there are some chapter problems, some practice problems that relate to this lesson. So you should do numbers 1 to 11 now. You can discuss with your group mates, and then I'll be in and out of the breakout rooms to make sure that you're on the right track or see if you have any questions.